Welcome to dynamics lesson. This is kinetics of particles, lecture 3. My name is Harmtedy. If you don't have lecture 2 and 1, you can ask, then I'll send. Yeah, so today we're looking at planar kinetics of planar kinetic energy of rigid bodies, and then at the end of this lesson you'll be able to develop the formulations for kinetic energy of a body and define the various ways a force and a couple do work. And then you should also be able to apply the principle of work and energy to solve rigid body planar kinetic problems that involve force, velocity and displacement. And then you should also be able to show how the conservation of energy can be used to solve rigid body planar kinetic problems. So let's quickly move on into serious business. So the first thing that we're going to start with is defining kinetic energy. What is kinetic energy? So kinetic energy is just defined as the energy that an object which is in motion has. So if an object is moving, it has a velocity and it also has mass. To say it has kinetic energy, it has a component that we call kinetic energy, meaning the moving energy. And then if you want to develop a kinetic energy, if you want to develop kinetic energy when the body is subjected to translation or rotation about a fixed axis, let us look at this diagram that has been given here. So of course we all know to say kinetic energy is given by half mv squared. V is just the velocity at which the body is moving, and then m is just the mass of that given body. So this is the general formula for kinetic energy, but this can be transformed into many other formulas that we're going to discuss. So when you look at this body here, we can see to say this body which is here, though it's moving in the velocity in this direction with a velocity v, and it's also rotating with an angular velocity omega, and it also has a translation or rather it also has a point which is x, y. The kinetic energy of the entire body in this figure can be determined by writing an expression for each particle of the body and integrating the results. So what they're trying to say is that, for instance, if you have a body of mass m, now to find the kinetic energy of this body, you simply just take a small mass which you call which you are going to call dm, and then after finding this small mass, you integrate this mass. Of course there's also velocity which is v squared. So this is what is just here. Okay, so let's quickly move on. And then this integral sign, sometimes it's also sometimes you can describe it to be the summation of small units of a given thing. So when you integrate, you are simply finding the smaller units and then the sum of those smaller units. Yeah. So let's quickly look at this same equation. So this equation, which is the previous equation, this equation you can see here, it can be expressed in terms of the velocity of a point P. So let us look at this point. This is point P, and then we're saying the same equation that we're looking at can also be expressed in terms of the point P. So how can you express this when considering this P, or putting into consideration this point P? So first of all, what you need to do is you find the position vector for r. So the position vector for r is just going to be given by, we know to say the distance in the x is x, and then since it's a vector, meaning we have our I there, then the distance in the y is y, then since it's in the y, we'll put our j there. And then after finding that, you now have to find, let me just show you this. After finding the position vector for this r, then you now have to find the velocity, with reference to the point P. The velocity of this object here, this object, this mass, with reference to point P. How do you find that? We know to say this object, we consider that this object has an angular velocity which is omega, meaning it's also rotating. So when it's rotating, you introduce another component which we call omega, but this omega will consider that it's in the z-axis, and for that reason we're going to give it a position vector k, and then which is just here, and then this k lambda, this k omega, you simply just multiply it with this r in order to find its velocity. So we know to say velocity v is just given by r omega. So this is the reason why we're finding the cross product of r and omega in the z-axis. Yeah. So after that, you can now write v in the vector form. So we know to say for you to find v, you have vp. For you to find v by using vp, by using the velocity at this point, vp is just the velocity at this point. You can use the vectors where you just say vp plus this same vi that we had found here. Then when you add the two, you are going to get the velocity vi. So in other words, we know how you add and subtract vectors. When you know that to say this vector is going this side and that vector is going that side, you simply add this plus that to find the magnitude, which is this vector. That is what is happening there. And then from there we can express this vp in its components as well. You can see to say this vp is not just in the x, it's also not just in the y, but it's somewhere like this, meaning it has both components, the x and the y components. Okay, I don't know why it's playing itself. I think I need to look at some settings. Yeah. So from there, you express vp in terms of its components, which is vp in the x-axis, vp in the y-axis, and then this r this vp, we add it now, which is here. So this vp we found to say is this, so we put it that side. So after adding it, we can now simplify it by saying, by putting the i's together and the j's together. We know that when you multiply this k times I, you get j. When you multiply k times j, you get I. So this is what is happening here, and then you put them together. Yeah, so you are going to put them together. So when you simplify by multiplying this, when you simplify by getting the cross product of this times that, you simply now just have to put the i's together and the j's together. Then you find your answer. So when you substitute this equation 7 into equation 2, so our equation 2 was just this equation here. So when you substitute this equation, the previous equation into this equation, you can agree with me to say this v squared can first be simplified. We know to say v squared is just the same as v times v, and then we know to say our v, we just found it, which is this one. So this one, you have to square it. So when you square it, when you square this, you are going to have that, and then from there you simplify it in that format, and then the final simplified version will look like that. So when you simplify it, you are going to have this, and then so here we're just trying to derive a certain formula. So when you simplify it, you are going to have this, and then this, when you replace it, you put it there, it's going to give you this. So don't worry about what you are seeing here. It's just it's not even a complicated formula. Just look at this, the integral of dm v squared, meaning this is the part. You just integrate this. In short, we've just put this whole formula where there is v squared there. So when you put it there and then you distribute, you multiply it with this integral dm, the integral of dm, you multiply it throughout this same expression, and then this is what we're going to get. And then here, when you look at the first expression here, this is just the translational kinetic energy. And then when you look at the last part here, this is the rotational kinetic energy, if you look at it properly. And then when you look at these part here, these are just points. They're just showing you the center of mass of an object. So this is what I'm just talking about, to say the first integral on the right represents the entire mass m of the body, since this y bar m is just equal to that, and then this x bar m is just equal to that, and then the second integral and the third integral gets the body center of mass g with respect to p, and then the last integral, which is just this part here, is just the last integral represents the body's moment of inertia ip computed about z passing through the point P, which is just this part here. Here they've introduced I. So as a special case, if the point P coincides with the mass center G of the body, then y bar and x bar is going to be equal to 0. So when this is 0 and when this is also 0, and this only occurs when the point P coincides with the mass center G. Let me explain a bit on this one. So when this is 0 and this part, when this is 0 and this is 0, this whole part will be considered to be 0, meaning you are just going to remain with these two. Yeah, you're just going to remain with those two. And then this is how your formula is now going to look like. It's going to look like this one. It's going to be this formula. Then from there, we can note to say both terms, we have also to put in mind to say both terms are supposed to be positive. And then since Vg and omega, which is the angular velocity, are squared, then the first term represents the translational kinetic energy. This is what I talked about. The first term represents the translational kinetic energy referenced from the center of mass, or from the mass center. And the second term represents the body's rotational kinetic energy about the mass center. So I talked about this on the previous slide. And then let's look at the application of this formula now. How and where can we apply this formula? The first application that we have is in translation, meaning when the body is moving, whether in rectilinear translation or curvilinear translation, you can still apply this formula. So when you talk about rectilinear, we're simply talking about a mass which is moving just in a straight line like that. All the particles in a given mass are moving in the straight line. And then when you talk about curvilinear, we are simply talking about maybe like something like a projectile, where the masses are moving in a curve. In a curve, they are moving like that. The particles in a mass, in a given mass, are moving in that format. So this is what I'm just trying to explain. And in both cases, in rectilinear and curvilinear, just note to say the angular velocity is equal to 0, because there's nothing that is rotating about a given point. And then the kinetic energy of the body is therefore given in the equation as this. So meaning if our omega here, which is the angular velocity, is 0, meaning all this part is going to be 0, we just remain with this part. So in either rectilinear or curvilinear, or generally in translation, we just use this part to find the kinetic energy. So where you are going to be finding T, as we are going to be solving questions, just not to say it's kinetic energy. And then let's also look at another application. We can also apply this same formula when you're dealing with a rotation about a fixed axis. So when a rigid body rotates about a fixed axis passing through a point O, like what is in this figure here, the body has both translation and rotation energy as given in the equation 4. So in other words, the equation can also be applied when you have a body, when you have a mass that is rotating about a fixed point O. Yeah, so when it's rotating, just know to say there we have both translation and rotational kinetic energy. So meaning the whole formula is going to be used. None of the terms in this formula will be zero. So the body's kinetic energy may also be formulated for this case by noting that Vg is equal to Rgw. So this is just a formula that we all know to say the translational velocity. Translational velocity is just equal to R times times the rotational velocity, yeah, which is just omega. Then from there we can now say T is equal to that. When you replace Rg where R omega where there is V squared there, and then you simplify it, you come to this as your final simplified version. Then from there you can conclude now to say, or rather by using the parallel axis theorem, the terms inside the parentheses represent the moment of inertia O. So when you look at this part here, when you remember what we discussed in the previous lecture about the parallel axis theorem, this part represents I about O, which is just the so this part represents I, which is just this one here. It represents the moment of inertia about the point O of a body about an axis perpendicular to the plane of motion and passing through the point O. So this part here, when you use the parallel axis theorem, it just represents IO. So from there, from the above derivation, equation 1.3, which is this one, will give the same result as equation 1.2. Since it accounts for both the translation and rotation kinetic energies of a body. So when you use this formula here when solving a equation, you also use this formula when solving a equation, you get the same answer, because they all talk about both translational and rotational kinetic energy. So which other application that do we have? We also have an application. Rather, we can also apply the formula when you're dealing with a general plane motion. So what is this general plane motion? When a body is subjected to general plane motion, it has an angular velocity and its mass center has a velocity Vg. Therefore, the kinetic energy is given in the equation below. So the kinetic energy will still be the same. So general plane motion is just similar to what we previously just discussed. Meaning the body has both translational and rotational kinetic energy. So this equation can also be expressed in terms of the body's motion about its instantaneous center of zero velocity. In statics, remember there was a topic which you were introduced to, which involved the instantaneous center of zero velocity. For instance, when you have maybe a wheel like this, then you have something that is leaning on it, and then maybe this is something like that, then you have this point there, it's fixed somewhere there, and then you also have a wheel there, and then let me do this. So when you're finding the instantaneous center of zero velocity, you can simply just do this. You can have this. I don't know why it's playing itself. Okay, and then you also get that. So where they meet here is the point that you are going to call IC. Okay. So that point is just a point where the velocity is considered to be zero at any instant or at an instant. So you can express this equation in this format as well. You can use the instantaneous center of zero velocity to find the kinetic energy of a general motion of or of an object that has a general motion. So where IC is the moment of inertia of the body about its instantaneous center. Okay, let us now look at this. It looks like a new topic, but it's a little bit connected to what we're discussing. The work of a force. This one is simple, so I'm not going to spend a lot of time here. So the work of a force. What is the work of a force? So the work of a force acting on a body, and the body moves along a path as shown in the figure, is given by the equation that. So this is just we all know the equation for work. What is work? Work is just force times distance. Now in this case we're using u to represent F, or to represent the work of a variable force. There is also what we call the work of a constant force, or there is also what we call the work of a weight. There are a lot of works that we know. So here we're discussing the work of a force. So we've started with the work of a variable force. So when a force is varying, so consider the r to also be varying. Consider the r to also be varying. That's the reason why we've used the r there instead of just saying force times distance. So this force times distance is normally used when a force is constant. So here the force is varying. So these are just formulas you need to master. So here theta is the angle between the tails of the force and the differential displacement, and the integration must account for the variation of the force's direction and magnitude. So the second one that we have to look at is the work of a constant force. So if an external force Fc acts on a body, like in the figure, this figure 6 there, we have an external force acting on the body and maintains a constant magnitude force and the constant direction theta, while the body undergoes translation s, then the equation 16, which is this equation can be integrated so that the work becomes that. So this is what I was talking about. When you're dealing with a constant force, you just say work is equal to the force times the distance. But the reason we have this course is because the force is not acting from this angle. It's acting from it's not acting at 0 degrees or at 180 degrees. It's acting at a certain angle, which is called theta, from the 180 degrees line. So this is the reason why we have a component of a force, which is F cos theta. But otherwise, when it's acting in the straight line with its direction, then you just say force times the distance. Okay, so let's now look at the work of a weight. So the weight of a body does work only when the body's center of mass G undergoes the vertical displacement Y. If this displacement is upward, the work is negative, since the work is opposite the displacement. So what they are talking about is just this. So if the work, for instance, if this body is moving up, if it's moving upwards, and then note to say the work is going to be negative, and it's given by this formula. The work of a weight is just going to be UW, which is equal to negative W times Y. Okay, so this W is simply just the weight times the distance which the body has moved going up. So likewise, if the displacement is downward, negative Y, the work becomes positive. In both cases, the elevation change is considered to be small, so that weight which is caused by gravitation is constant. Yeah, so that one is self-explanatory. So let's also look at the work of a spring force. So the work of a spring force. If a linear elastic spring is attached to a body, so this these notes here are just talking about this. If a linear elastic spring is attached to a body, the spring force Fs is given by this. We know this, which is K, which is the spring constant times the distance it has moved. Then this is the stretch distance. Acting on a body does work when the spring either stretches or compresses from S1 to a further position S2. So in both cases the work will be negative, since the displacement of the body is in the opposite direction of the force. So this one is also self-explanatory. You can just read through these notes. They are simple and straightforward. So this is the work is just given by this formula. Yeah, the work is just given by this formula. The reason why this negative is here is because it has been explained here. Where is it? Yeah, this statement here and this statement, they are talking about this negative. Okay, the work of a couple moment. So this one is straightforward as well. When you talk about a couple moment, we're talking about maybe something like that, and then we have two forces acting on it, the force from this side and that side, and it's rotating about a fixed point there. So how can you find the work of this? You just simply add the forces F1 and F2. So F1, we know to say F1 is if this distance is r, meaning F1, meaning this first part here will be, will just be r divided by 2. This second part will also be r divided by 2. So if these forces are equal, if F1 and F2 are equal, we can simply add this, and then when you add this, we'll just get to have F. So when you add this part and this part, you get F r d theta. This is what we're going to get. So once you have that, we know to say force times distance can also be considered to be a moment. Moment is just equal to force times the moment arm, which is the moment arm distance, which is just r. Okay, so this is what I've just been explaining here, and these are practical examples on the moment. Alright, so this is also talking about the same thing, and then it's saying the work is positive when the moment and the theta have the same sense of direction, and negative if the vectors are in opposite sense. Yeah, so this one is straightforward. It's saying if theta is going this side, which is a clockwise direction, and the moments are also going in a clockwise direction this side, consider your work to be positive, and then when they are in opposite directions, your work is going to be negative. So when the body rotates in the plane through a finite angle theta, measured in radians from theta 1 to theta 2, the work of a couple moment is therefore this. So when it's moving, when it's rotating, when the body is rotating, meaning it's not stationary, when the body is rotating through a finite angle theta, the work of a couple moment is just given by the integral of m d theta. You just integrate m d theta, and then with respect to theta, of course, and then you put your limits from theta 1 to theta 2. Yeah, so this is straightforward as well. So if the couple moment m has a constant magnitude, then this is what we are going to have. So if the couple moment m has a constant magnitude, meaning it's not the magnitude is constant, meaning it's not changing, it's not variable, you can use this. So instead of integrating, you are just going to use this. You're just going to say theta 2 minus theta 1 and then multiply by m. So this one is the rotating body, and then this one is a constant. It has a constant moment m. So I think this is the end of the lecture. Oh, there is also this part. So this part, which is the principle of work and energy, this one just combines the two, which is the kinetic energy and the work of any given body. So if you have been given a body which is having both kinetic energy and work, or you are requested to find one of these, you can simply just add okay, let me just read through the notes. By applying the principle of work and energy developed earlier to each of the particles of a rigid body and adding the results algebraically, since energy is a scalar, the principle of work and energy for a rigid body becomes this. Yeah, so this equation states that the body's initial translational and rotational kinetic energy plus the work done by all the external forces and couple moments acting on the body as the body moves from its initial to its final position is equal to the body's final translation and rotational kinetic energy. So you should also note that the work of the body's internal forces does not have to be considered. These forces occur in equal but opposite collinear. So the work of internal forces, remember what I explained in the first lecture, the work of internal forces, we do not count them when you are finding the summation of forces. Why? Because they are in equal and opposite collinear. They are equal and opposite collinear pairs, meaning they cancel each other, so that when the body moves, the work of one force cancels that of its counterpart. Furthermore, since the body is rigid, no relative movement between these forces occur, and so that the internal work is done. Okay, and then you should also note that when several rigid bodies are pin connected by inextensible cables or in mesh with one another, equation 23, which is the equation that we're just from discussing, equation 23 can be applied to the entire system of connected bodies. In all these cases, the internal forces which hold the various members together do not work and hence are eliminated from the analysis. So thank you very much for watching today's lesson. So if you have not understood, you can repeat it, you can replay it again, try to see where you don't understand, and then if you have any questions, you are free to contact me on WhatsApp. My lines are in the description below. See you in the next lesson.